institution, and he will present us his talk about HPC LBM for the simulation of living organisms. It's a real pleasure for me having him today, and enjoy his presentation. Please, Giorgio, the floor is yours.
Okay. Thank you, everyone. I'd like, first of all, thanks for an invitation of all the DSD organizing committee. I think that everything, the setup.
Yes, it's starting, yes.
Is starting. Let's go to the presentation. Yep, start from the beginning. Again, full screen. Presentation. Here we are. Okay. Here we discuss about the simulation described yesterday by Giacomo. I think the title could be a little bit misleading, because essentially I present the work done to allow this kind of simulation. It was my personal one of the biggest I ever done, because we are performing more than 50 billion grid point simulation. So I don't spend too much time about physical issues. The idea is to share the experience and what the aspect that we have to face to perform this kind of simulation. And I'd like to underline it's still evolving work, because we want to do more, and we won't try to do also best again. And just to give a picture of what we can be done using today machine. As previously described, we want to perform a simulation of the flow, a dynamic flow, around the so-called Venus flower basket, this kind of sponge made with silica, we can see on the picture on the left, that present well-known properties of stiffness, as described in different articles. But it's not clear if the particular structure, as you can see, is an extremely beautiful one, is due only to structural issues, or also depends on as a fluid dynamic effect. As happens usually in nature, any particular configuration has a different value to survive. And this on the right we have the structure of the flow, the simulated flow. This is what we have produced. I don't want to enter too much in details because we are still working. I think I like to underline that probably one of the most stressing things to do was to collect all the information to get beautiful figure due the size of the problem. But for example, I'd like to underline, I hope that the pointer can be seen, that the seems that we all the plankton that enters inside the sponge tends to go down where there is the animal and feed. So this seems to be also a structure good for a sort of trap for plankton, but it's just an idea that we have still to explore. The main figure of the sponge that I presented you before is this. It's a very huge lattice. The radius is about 100 grid points, so we have a very huge domain just to avoid finite side effect as much as possible. For the computational point of view, we ask for about 7 terabytes of RAM, and each dump is 3 terabytes. The performance expressed in megalattice update per second is 680 giga loops. This means in floating point around something less than 200 teraflop. This is the performance of the full simulation. So considering only also the few dumps of the whole population, all the diagnostic, all the file for visualization, and so on. So it's not the single kernel performance. And this is some number that we have simulated this test case using Marconi 100, that was the new machine here in Cineca, in Italy, and is at 9th position of top 500 for what it worth. And we use a part of that, up to 512 graph GPUs. And so 5 different algorithms are performed, and for a quite long time step to have enough statistic. These are the key points of the code. It was a single relaxation time, very simple lattice, and as was noted yesterday, we have a brute force approach. There is no grid refinement, even if probably there is a lot of waste of memory outside the main flow. But this choice was done for different reasons. The fact we have access to the huge number of CPU hours for a limited time. The second, that start to use, because we have still to implement, the non-uniform grid. It's very, especially for validate the flow, it's very, very time consuming. So at the end, at the beginning, we have decided, as you used to say, first work, then run. So even if there is a waste probably, but was used to stress all the aspects. As I told you, we use a brute force approach. There is different reason. The fastest is to have more information. The idea is first work, then run. And also to understand all the features to perform this kind of big simulation. Then, as you present after, we have planned to move to use a more clever grid refinement. But at the moment, it was just almost for me challenging to perform this kind of a simulation, even if at the beginning we have no clear idea where you have to refine your codex, your grid. And also, it was used to perform a check of performance and portability, because this code was run, and the result shown here belongs to using completely different architecture. This is important in the evolving with the evolving kind of machine for Exascale and so on. In the next slide, I've performed a test to understand which is the limit that probably we can reach with this implementation on this kind of machine for a more simple test case driven cavity without a huge number of data dump and diagnostic, only to check that everything was fine. So we have not a number somewhere. And we found that we can reach with the machine, Marconi 100 machine, having access to the full machine, something around 8 teraloops for a 4 billion grid point. In this configuration, 40% of the time is spent in communication, so there is still room for improvement. The question that we have to ask every time is the best that we can reach, so we have to work again to go faster, and how these figures are obtained, and is coherent with the hardware that we have. Okay, how I can check velocity? This is a personal point of view, but flops are not a good metric because it depends too much about implementation and if all the operations I perform are important or not. A good metric is a megalattice update per second that is independent how many flops I perform, but really how much my particular application can perform, and I compare the result with other machine, with other code, with other people, if the test case is similar. The aspect important to underline is that today machines are present completely different performance figure according if you are floating point limited or bandwidth limited. And different code could have different aspect and behave in different way. It's important to have a model to compare the performance with the estimated one to understand how far you are from the limit. A model that I use that quite easy is the roofline model, in which it's a throughput-oriented performance model and doesn't track times, but rate, and in general is independent of the architecture of the underlying instruction set. A very, very brief description is here. I want to have the total flops expressed in terms of the so-called arithmetic densities. Also, this means the ratio between a floating point operation that I have to perform and the byte, not the single byte, that I have to move back and forth to perform this kind of simulation. With this ratio, we can see that the performance of a CPU has this particular behavior, sort of roofline. On the left, we have limited by bandwidth, because I have to perform few operations relative to data that I have to move. On the right, we have flop limited application, in which that we have not worried too much about data to move, but how many operations I have to perform. Keep in mind that for ranking of top 500 supercomputing list, we perform a test that is HPL, high performance link pack, that is essentially a flop limited application. So we're ranking a machine able to perform big matrix multiplication, but from if they are bandwidth limited, this metric could be not good enough. This behavior is the behavior for a GPU, for NVIDIA V100. And now we can try to understand how our application behave in the real world. We have a measured bandwidth, and our code is bandwidth limited. We have for each grid point, if you try to make yourself all possible optimization and remove any common sub-expression, that more or less for each grid point, we have to perform 250 floating point operation. And to perform this, we have to move 19 operation back and forth. In this case, I use for single precision. I'll describe later the reason for that. This means that we have to perform this peak performance and this about for each single GPU, something more than 5,000 megaloops. Then we can perform in our code how far we are from this value after have check with hardware counter, for example, that is assumption of the floating point operation and the bandwidth data movement are coherent, obviously. If this assumption is not correct, all the information are wrong. We can see that for, again, simple driven cavity, 1000 time step, single precision with on GPUs, sorry, I forgot to write this aspect. For different sides, we can find that we have, as the size is big enough, 3.5 megaloops achieved. This is about 60% of the real performance achievable according to this roofline model. This means that this is the arithmetic intensity that we found. Here, the value that we found. So we are not so far from the limit. This is a naive roofline model because I've taken account the bandwidth with the RAM. If we take in account effect of cache, we have different lines. It becomes a little bit more complicated. But at this point, we have the information well. We are not so far to the limit, so could be a good result. Then a little deviation about parallel toward exascale machine. Actually, the main trend, unless the new top 500 supercomputer, Japanese Fugaku, are heterogeneous computing. Many nodes with some accelerator for nodes. Order of nodes, it's 10,000, or without accelerator, we are more than 100,000 nodes. There is different way to parallelization. There is vendor success, different language, CUDA from NVIDIA, IP1API from Intel, but essentially it's C-based. For the precision, data parallel C++. For Fortran code, actually there is very few there is only way to have portability to use an hybrid parallelization using OpenMP, eventually OpenHatch, or the GPU version of OpenMP for inside a single node. An aspect that an hardware can be removed in a very fast way. The story of Intel Kenel that after the second generation, Intel decided not to develop again this kind of supercomputing. And so all the effort done to optimize on this architecture was in a sense Western, but it's not true completely. And so the idea is we have no idea what will be the next supercomputing. You have to be ready to change the code according to the code, to the machine that you have to run. So performance portability can achieved is a little bit expensive. You need a systematic ad hoc code modification. This means that one important thing is that you have a clever way to validate the code, because you have probably many times to start again to verify that everything was fine. And this is a very time-consuming operation. So if you are get ready to have some procedure to check the quality of your result, you can reach a sort of performance portability. Another thing to do is that this is a famous sentence from Nut. It's a very famous parallel programmer, but it's maybe much more known because it was the inventor of the LaTeX typesetting system, so that every one of us is using, is that premature optimization is the root of all evil. This is true if you think too much about optimization, but the problem is actually there is 100 different ways to write a code to implement an algorithm, but 99 are slow or very slow, only 1 or 2 are efficient. So if you start in the wrong way, probably you have to rewrite from scratch your code at the end. The reason we know the sentence of Nut was correct, it was done after late 80s, in which there is a systematic increments of performance due to the fact that we are able to increase in a very fast way frequency. But from 2000 and half of the 2000, this gain is not more sensible. Actually, when you buy a new machine, you have no particular increase on performance, essentially. You have to put you have more transistor for strange unit, for much more core, and so the optimization you have to do by yourself. This is an old result of an emailing list in which there are information that's what is a success to increase your code without going to parallel computing. And some of this I'll present. The idea is there is a different tricks, but there is the coding style that seriously can affect performance. I've seen many lattice Boltzmann code, and there is a way natural, because it's a really compact way, for example, to compute velocity. Is what is described here. You can see that it's very compact, it's very easy, but it's really inefficient. You can expand the same operation with the same result without reducing number of operations, because most of this, all of this multiplication with the CX are essentially simple. We are make a multiplication for 0, so no result, -1 or +1, so it's a simple sums. So all this operation, all these flops, and all these loads can be reduced by a serious factor, and this can have a serious impact about performance. Because time is running, I go quite a little bit fast. There is some serial standard tricks, so you have to check about data allocation. Usually this one, the first one, is more efficient. Keep in mind that you have the variable you have to integrate is the population, not velocity or density. So any conversion or storing memory can be really, really expensive. So you can use only when it really needs. Using function subroutines are very easy for programming, but can be time consuming because, as you showed before, many operations are not really multiplication for 0 or simply sums. You have to expand the loops, and as you done by yourself, the so-called common sub-expression elimination is something that the compiler do, but it's better to do by yourself. And avoid pointers as possible, because can inhibit some operation as a vectorization that give you the good performance. This is an example using Intel Skylake for a driving cavity in serial operation for double precision. I use the pointer to swap between population because I use the so-called fused of push-pop operation in which everything was, there is only collision subroutine in a sense. I read from a class of population, I read back the result on the other and then swap what is all the good news and so on. And if I tell to the compiler, keep in mind that pointers are contiguous so you can perform a lot of optimization, there is quite a factor, slightly less than factor 2 of improved performance. Here there is a mistake, sorry. What is B is A and so on. I have to fix, but again, with this success to the compiler, you go faster. This is more impressive if you perform a very long step of operation from one kind where it's not cache efficient, more cache efficient, the so-called fused. We can see there is a drop in performance in both architecture, but it's because with the use of the pointer, also vectorization is inhibited. I can force vectorization, and up to this level, it's completely independent from the hardware. Forcing for a single architecture instruction set, there is a good boost in performance. And again, using single preparation, we have an again boost in performance. This means that up to a factor 10 can be reached only on serial tricks. So it's something that a success to spend you time at the beginning of your writing the code is important. Even OpenMP, for example, for KNL, we have a 9-factor improvement for without vectorization, A, without vectorization, so removing any kind of vectorization is a key point for this kind of architecture. Standard with the third, the C is forcing hardware instruction set, and again for the success to the compiler, there is data coherent. So we can see there is quite a 10 improvement. Also MPI, there is 2 different communication I can use, or send receive or not of non-blocking. And for IMPR count, we have that non-blocking more efficient, even if we not perform the so-called overlap with data communication. Is the system is more ready to manage this kind of communication. And for GPU, this is more evident using also a low level of MPI ranking. So we are talking about 50%, which the weight of the communication is in a sense increased by factor 2. And there is also a class defined 33, so something that can be used in particular test case. For we know that all these kind of machines essentially are able to perform much more single precision than double precision, and in the future also half precision for other issue. And it's something that you have to explore if it's good enough. This is a for our simulation. The same test case uses single and double precision. You can see no significant difference. If you go in detail, there is obviously some difference, but not so much, especially for here, there is also still a periodic. This allows us to choose a single precision. For this reason, that using KNL, for example, we has essentially a factor slightly than a factor 2 in terms of performance, in which the MP time is reduced and also the collision time is reduced. If a single is not good enough, you can try a sort of mixed precision, which all the operations are performed in double precision, but that are stored in single precision. While for this approach is not so good for the KNL, in which there is you go faster, but there is a serious decrease in terms of performance. For a single GPU, we can see there is not so big difference without single and mix. So this can be a good solution to work about on this. Oh, sorry. Okay. Here, a result for a driven cavity in which all the lines are collapsed. So seems quite good between single, double, and mixed precision. If you go in detail, there is a slight difference between single and double, while mixed behave more or less for this case similar to the double. So my idea is to check what is good and look for which is the best solution, the best ratio between quality of the result and velocity, because we are talking more or less in a factor 2 and something that you can
Giorgio, you have 5 minutes. Okay.
Check. Okay. So the lesson learned from all this situation, you have to be ready to change your code many times, because machine evolve, also compiler evolves, ideas evolves. There is also, it's not to be fixed on a particular configuration or particular situation. You have to modify many times your code. This means to use a code repository, to create a testing suite to check the result every time, because shit happens and obviously some mistake can be done and you have to check it as soon as possible. And always profile your code, because sometimes you find different strange behavior, and from this strange behavior you can understand what goes wrong if the machine, if your assumption not correct, and also correct your code from physical, but especially for performance point of view. You have to know to face what is a computer, what is a compiler, what it works, all the flags, and so on. So, if possible, play with different compiler, CPU, and so on. Not rely only on this different computers. The porting could be very, very, very complicated. So, it's a very long way process. And especially, look always with other people do. There is always something that you can learn from the other. And what is defined also KISS in computer science, keep it simple, stupid. And that's something that I always used to say to myself, because this, if you want to perform a big simulation, you have to tune for the machine. And if it is simple, it's much more easy. If you have a complicated structure, then the impact to optimize the code could be very, very, very expensive. So this is a famous document about full people about parallel computing. I hope to be as honest as possible, unless the point 12 that I show some pretty figure. As also Giacomo presented last time, these are obstacles that we have to perform to check the simulation. Here we have this beautiful video. Okay. You can see correctly the video? Is everything fine? I have no feedback.
Yes, we see it. It's a little bit scattered, but it's not continuous. But we see the images.
Oh, sorry. I think it's due to my internet connection
I
at
think that
home.
it's
I
quite
was
clear
not
enough. Yeah, it's quite
efficient.
clear though.
Okay, here this I'd like to not to discuss about the physical properties that was also described yesterday by Giacomo. Just I'd like to underline the fact that the three of these four simulations performed using Intel KNL, and the bottom on the left simulation are performed using GPUs, so completely different architecture. The code is exactly the same. What have changed is only the compiler option and few pre-processing flags, and the result I think is quite you know, not impressive, but you have idea to perform something interesting. I like very much this kind of recirculation for the simulation of the network with the region. That seems quite interesting. I think that could have an impact in terms of food for the sponge. Okay, but it's my assumption. Let's go back to the presentation again. We have already finished. Okay, let me move to the presentation again. So, further step, working with different geometries, put all sponges again, and also to face the problem of grid refinement. That is something that we have to put inside, but as you understand, you have to use pointer, you have to be clever. This could have serious impact in terms of performance, using a huge number of GPUs. Some advanced tricks, we have fine-tuning on the hardware. This is mandatory because this machine is new and you have to learn exactly how it works. And something you have to work on about 40% of MPI communication, so overlapping communication using advanced feature MPI3 like one-sided communication that can help you to have a better balancing between tasks. I have to ask to say acknowledge a different person, Giacomo, Vesselin, Marcello Sega, and also colleague Cilega Vittorio for successfully very important compiler flags. There was the one expert on that. And some references about what we have told before. And thank you very much for attention. Okay. I hope to be on time.
Yes. Giorgio, thank you very much for this really inspiring presentation that summarized all the quest that we have done in the last almost 2 years to perform this simulation. So if there is some questions from the audience, we have a reservation from the audience from Anastasia Perepelkina. Did I say it quite right? Anastasia, do you have a question? Also, if you do not hear from Anastasia,
Hello?
we... Oh, okay,
Hello,
okay, please.
Okay, I
Yes.
Okay, thank you for the interesting presentation. I actually really like your slides with the roofline model. Have you researched into the methods to increase the arithmetic intensity, like merging several layers in time? It's called maybe temporal blocking or diamond blocking, or such similar algorithms.
Okay. The question is correct. It's the fact if spend some time to increase my architectural intensity, arithmetic intensity. Yes, I played with a little bit with blocking and so on, but few years ago, but was not successful. Again, every time that you change architecture, the idea is to perform a sort of check if a previous assumption was more efficient or not. For this kind of simulation, this configuration, I found no particular improvement, also because it's a very, very simple data. They use the pointer only to swap without population. So seems to behave quite efficient. Some operations they have done, but again, in general, if you have to modify the arithmetic intensity, you have to modify deeply your algorithm. It's a very time-consuming operation because you have to, again, to check everything. So what I suggest is always to do the best at the beginning, then at the end of your process. Else it could be too much expensive. The only way that I used for this simulation to increase arithmetic intensity is to move from single to double precision, in which you decrease by a factor 2 data movement, in a sense.
Thank you.
Okay, thanks. There is
You're
another
welcome.
question by Stefan Sitz. Are you there?
Yes, I'm here. Can you hear me?
Please,
Yes.
a quick question, if possible, because we are running out of the schedule, please.
Okay. So I was wondering about the impact of the language you use for your simulation or for the performance. So I guess you used Fortran.
Yes.
But have you tried? But have you tried to use something more modern, so to say?
No, I'm old guy. I start with Fortran 25 years ago with Sauro, and probably I'll die with Fortran, because this is not really too much a problem of language, you know. What is, I think, useful for Fortran is it's very, in a sense, old language, which has very important feature in the many reasons, but is the fact to be well-defined, not so flexible, allows compiler to work fine because they are much more rigid syntax. And then allows programmer not to try to make complicated stuff that very elegant but not inefficient. If you want to go efficient, this is my experience, you have to be simple, not to use very complicated feature, and to do by yourself everything that you can do. And let to the compiler do only that works on translating the code. And this is something that probably will be done also to the new version of the compiler, that what is a huge supporting using data parallel CA++, because fit well with this kind of architecture. So the idea is everything has to do the programmer and leave the compiler to do the dirty work. I think it's about 20 years, for example, they think about auto-parallelizing compilers, but it's nothing really efficient was ever done, and probably will never done. You have to do the work, dirty work. So I think that any language is important. The language you know best is the best computing language, because you have to do the dirty work.
Okay, Giorgio. Sauro, please.
Yes, just thank you, Giorgio, for the very nice talk. Actually, I was not aware of this detail. Let me ask you a nasty question. I hope I can afford that.
Yes, I know you.
So you might, no, I'm joking, but you were mentioning, rightly so, the exascale epoch that we are approaching. But as a matter of fact, I think we are still far. I mean, if I go, for instance, the machine we have been using, the Mac 20, what is its peak performance? And how much of it will you get? So we are still far from exascale.
Not so much, in the sense. The top one machine is the Fugaku machine in Japan, is the follow-up of the K machine, and it's claimed to have a sustained performance. About 4.5 exaflop, something less than half exaflop. Okay, but it's a sustained performance using LIMPAC and matrix multiplication. What you really apply in your code, it's still unknown. Marconi 100 is 9 rank 9. It's, if I'm correct, something about 20 petaflop peaks. And for my code, we have around 10% of the peak performance. And this is the ratio of a code. So keep in mind, the exaflop is a target for, ideal target is a political one. What are the really performance you have to gain is an open question. And the result is that you have to spend many time to reach all the performance.
Okay.
Okay, sorry.
Okay, thank you all for this interesting discussion, and we have to move ahead. Thank you, Giorgio, very much.
Thank you to you
once again for this very kind and inspiring talk. And we start our technical session. with Dr. Awane.
Yeah, I'm here.
Okay.